Good morning, dear students. As I told that equilibrium, concentration, that means equilibrium constant help us in three different ways. That is, it is applied for calculating or knowing the extent of the chemical reaction as well as direction of the chemical reaction. And today we will discuss about the third application, that is calculating equilibrium concentration. Equilibrium concentration is comprised of few steps. Actually, one or two numericals we have already done on basis of it, but as it is given in the form of theory, we will also discuss it over here. The step one is, first we are in need to write the balanced equation. When we say the balanced equation, that means on left hand side and right hand side, we have to balance the number of atoms which are taking part in the reaction. If not balanced, we need to multiply by stoichiometric coefficients to get it balanced. First step. Second step, make a table of concentration under the balanced equation. Under it means under the balanced equation. Now while making the table, what we are in need to start first. The first we need to write down the initial concentration. Now when I say initial concentration, it means initial concentration will be of the reactant first, because reactant will start first reacting. Then after the consumption of some of the concentration, we will get the concentration of the product. So at initial stage, the reactants will carry some initial concentration and initial concentration of the product will be 0. Then change in concentration, which is going to be equilibrium. Then we don't know that what is the exact concentration at equilibrium. But the next we are going to mention is the change in concentration, which is going to be happen or which is going to be taking place at equilibrium. And C is the equilibrium concentration. And the last is we need to calculate equilibrium concentration. These are the steps we have already learned and we already calculated the numerical. Here after this discussion also we will calculate, so it will be easy for you. Now to mention the initial concentration, we would be given some concentration, but for equilibrium concentration, if we are using a known variable, that is X, as a concentration of one of the substance that reacts on going to equilibrium, then use stoichiometry to calculate other with respect to the X. Suppose you are taking for any one of the compound X, then you have to keep in mind that others should be calculated with respect to that supposed variable. The third step is substitute equilibrium concentration in equation for the reaction to solve for X. Now after getting the equilibrium concentration, we will have to substitute the value which is to be solved for the X. And if here on solving the equilibrium concentration, after substituting the value, if we are getting quadratic equation, choose the answer chemically which is feasible. Because when quadratic equation is a form, then we know that we will get the value of X in two ways, either these or this. So as per the chemical equation, what is more feasible or what is more possible, that we are going to select. As you are selecting in maths, right? When quadratic equation, if you are finding length and everything, then length won't be negative. Suppose you are getting one X as negative and one as positive. Then what is feasible? That is means what is possible? Positive answer to select is possible because length won't be in the negative. So this is what here it is to be kept in mind, that if the equation is quadratic, we need to choose the answer which is chemically possible, or we can say which is chemically feasible. Fourth step is calculate equilibrium concentration from the value of x. And fifth is check your result by substituting the value in equation. So here, these are the 5 steps which help us to calculate equilibrium concentrations. And on the basis of these steps, let us here again solve. Not again, but let us here go through the solved illustration 7.9. 3 moles of PCl5 kept in 1 liter closed reaction vessel was allowed to attain equilibrium at 380 Kelvin. Calculate the composition of the mixture at equilibrium where Kc is equal to 1.80. So here Kc is given to us and the amount of the PCl5 kept in 1 liter is also given to us. We are in need to calculate the equilibrium composition of a mixture. So very first step is to write down the balanced equation. So PCl5 and reacts gives PCl3 plus Cl2. 1 p atom, Cl5, 3 plus 2. So it is balanced. Now second step, write initial concentration. As I told, at the initial only reactant will start reacting. So product will be just 0. So 3 moles at the initial will start reacting, and at that time the product is having initial concentration 0. At equilibrium, which is going to take place, there x mole will be the concentration, because we don't know exactly what will be the concentration of PCl3 and what will be the concentration of Cl2. So suppose if we say that at equilibrium, suppose this concentration is going to occur as x, then at equilibrium what will be the concentration of reactant? The concentration of reactant will be whatever the concentration initially it has, out of that it has consumed and got the product with this concentration. So now the left out concentration for reactant will be 3 minus x mole at equilibrium. Clear? And now putting the formula of our Kc, equilibrium concentration, which is already given also 1.8, which is equal to product of the products, product, that is multiplication of the products, divided by multiplication of the reactant. But here only one reactant, so no multiplication is necessary. Now putting the value or substituting the value which we have taken, then 1.8 is equal to x multiplied by x, that is x square, upon 3 minus x. Now as you are doing in, or as you have done in your 10th standard in quadratic equation, please cross multiply this, or you can say that from denominator take it over here on the left hand side, it will go to numerator. So 1.8 multiplied by 3.3 minus x is equal to x square. Open the bracket, 18 3s are 54, 1.8 into 8 5.4, 1.8 into x 1.8x. Form the quadratic expression, so x square minus 1.8, if I'll take here it will be plus 1.8, and plus 5.4 when I'll take on left side it will be minus 5.4. Now here I got quadratic equation. Compare the values of ax square plus bx plus c. So a here is 1, b is 1.8 and c is minus 5.4. We know how to find out the alpha and beta with the help of the delta value. But here we will go directly with the alpha and beta as taking x. So x is equal to minus b plus or minus under root b square minus 4ac. Right? In mathematics in 10th standard you were writing under root delta. And delta is equal to b square minus 4ac. So one and the same thing. Divide by 2a. So what is here? X is equal to minus 1.8 plus or minus 1.8 whole square minus 4 into 1 into minus 5.4. Putting the value of a, b and c, we will get over here under root 3.24 plus 21.6, that is minus 1.8 plus or minus under root 24.84 upon 2, and you will get x value as 1.59 molar. Right? Actually, I have written over here, but here I have kept empty so that you will exactly calculate with the help of your calculator and get the answer whether it is 1.59 or near to it, right? So that you have to find out. And so this is PCl3 is X, so it is also 1.59. Cl2 is also X, so it is also 1.59. So both the product is having 1.59 concentration and reactant is having 3 minus X. So 3 minus 1.59, it will be 1.41 molar, right? You please try to calculate, maybe 1 or 2 point difference will be there, but you must know how to calculate with the help of your calculator, right? And now, as we have calculated or we have achieved the formula to calculate the equilibrium concentration Kc, equilibrium partial pressure Kp, even reaction constant Q, and here we will see one more relation, one more combination of this equilibrium reactions, that is relation between equilibrium constant K, only K written because if equilibrium constant is for concentration it will be Kc, and if it is for partial pressure then it will be Kp. Then reaction quotient Q and Gibbs free energy G. Now please recall where we have learned about Gibbs free energy. Gibbs free energy is a topic which we have already discussed in chapter 6 thermodynamics. Energy which is free to carry out the reaction is termed as Gibbs free energy, right? If you have forgotten, I would like to refer you, please go through the topic of the thermodynamics which will help you again to recall back. But by the time it's a free energy which helps to carry out the reaction, and we can say it is free energy, that is delta H minus T delta S delta G is equal to delta H minus T delta S. So it is a difference in the enthalpy at constant temperature minus difference in the entropy. I think so now you would have recalled. The value of Kc does not, why we are in need to relate equilibrium constant and reaction quotient with Gibbs energy, because the value of Kc, equilibrium constant concentration, does not depend on rate of reaction, right? Kc is not bothered whether the reaction of forward is fast or whether the reaction of backward is fast. What is the rate, slower or faster? It is not bothered. It is bothered with C. C, that is the concentration. Multiplication of product with its coefficient as a power upon multiplication of reactants with its coefficient as a power. That is the need of the equilibrium constant concentration. So it doesn't need what is the rate, how fast the reactant is reacting and how fast the product is obtained or how fast the backward reaction is. It is not a need for it. It is only in need of concentration. But Kc depends on thermodynamics and mainly it depends on free energy. It does not depend on rate of reaction, but it depends on the thermodynamics, right? Now let us recall a few formation which we have already learned and discussed in thermodynamics. If delta G is negative, difference in free energy is negative, reaction is spontaneous in forward direction. And if we say that delta G is negative, reaction is spontaneous, that means it occurs on its own in forward direction. That means in reverse direction, in backward direction, the value will be positive. Another condition, if delta G is positive, reaction is non-spontaneous in forward, but it will be spontaneous in backward. As I told here, if forward is spontaneous, then backward will be non-spontaneous. Here forward is non-spontaneous, then backward will be spontaneous. But for it, delta G negative, delta G positive. And if delta G is 0, reaction has achieved equilibrium and there is no free energy left to drive the reaction. To drive, that means to carry further, to proceed the reaction. Let's see the mathematical expression for thermodynamic view of equilibrium. As earlier I told, equilibrium is a chapter which is carrying variety of formulas and variety of numericals. Right? At each topic, you will be having one more method, and as per that, you will be having that type of numericals. So here also, let us see the mathematical expression for thermodynamics in the view of equilibrium. So we know that thermodynamic delta G, as I told just now, few minutes back, delta G is equal to delta H minus T delta S. It is one of the formula with the help of enthalpy and entropy. Here is one more formula which we have calculated in thermodynamics, that delta G, difference in free energy, is equal to difference in standard free energy. Delta G degree is standard Gibbs energy. Standard energy, it means the free energy is fulfilling in the reaction when the reaction is carried out at the standard condition. Standard temperature 298 Kelvin, standard atmospheric pressure 1 bar, right? And that free energy is termed as standard Gibbs energy, that is delta G naught. R is the gas constant, T is the temperature, Ln stands for the natural logarithm, and Q here is, Q stands for reaction quotient, where reaction quotient is nothing but it is equilibrium constant at concentration. So Q equals Kc. Now delta G is equal to delta G naught plus RT ln, instead of Q, what we can have? Kc. So it is ln K. Here K only written because alter time it won't be there to calculate concentration equilibrium. It may be calculating partial pressure equilibrium. So at that time it will be Kp. And for concentration it will be Kc. So here written only K. If concentration, you will mention Kc. If we are asked or if we are in need to calculate partial pressure, then it will be Kp. Now as at equilibrium, delta G is 0. So here at equilibrium, if we consider that delta G is 0, then 0 is equal to delta G naught plus RT ln K. Taking this RT ln K on left hand side, we will get delta G degree is equal to minus RT ln K. Right? And now taking the natural logarithm, because we are in need to convert natural logarithm to the logarithm. So we will separate the natural logarithm term, and that is ln K is equal to minus delta G d naught upon RT. Right? Taking antilog on both the sides, because we don't have natural logarithm table. We have logarithmic table, but natural logarithm we don't have, and that is why in thermodynamics, if you have remembered, when we have taken away log, that is natural logarithm, we have added one number, one value, that is 2.303. Right? So here we will be multiplying antilog on both the sides so that the logarithm value can be attained. So here I have written antilog of ln K. This is natural logarithm. If I am writing ln K antilog, then it is equal to log K. And if log expression is to be cancelled, then that value will be written in the exponential form. Right? Log of a to the base x, then log of x to the base a we were writing, that is a raised to x. So here also this log k is mentioned in the exponential form as K is equal to e raised to minus delta G degree upon RT. So this natural logarithm when converts to log, it will be log K to the base A is equal to e raised to x. And here this K will be minus G delta G degree upon RT. So this is the formula which will help you to calculate equilibrium concentration, right? Here also certain conditions are there. Reaction spontaneity can be interpreted by, first, if delta G degree, this one, that is delta G naught, is negative, then what will happen? Delta G negative and total term is also negative. So negative will be positive, and due to that K will also be positive. If delta G is negative, delta G degree by RT is positive. I just told why positive. Because delta G itself is negative. So putting value here negative, positive. And K is positive greater than 1. Then K is equal to product upon reactant, as we know for the concentration, equilibrium concentration, which implies spontaneous reaction. If the value of K exists as greater than 1, then it implies, that means it gives the idea that the reaction is spontaneous reaction. And if delta G degree is positive, then minus delta G degree by RT is negative, because this will be positive, negative. And therefore K is negative. Negative, it means it will be less than 1. Positive, it will be greater than 1. And so reactant is greater and reaction is non-spontaneous. So this you have to keep in mind. Delta G naught is negative, then here it is positive, because negative will be positive, and then K is greater than 1. And here little difference, that is K is less than 1, right? So this is about the relation between equilibrium constant K, reaction quotient Q, and Gibbs energy delta G, right? And now the new topic we will see in the next video, which are the factors affecting to the equilibrium of the reaction. And before that, to solve numericals also we will see. So you will come to know exactly how to use the formula. By the time, thank you.